Ladies and gentlemen, allow me to take you through Euclidean geometry. In this video, I will be sharing you the techniques on how to deal with the Euclidean geometry riders, on how to solve Euclidean geometry riders. Let us look at the example given. In the diagram, ABCD is a cyclic quadrilateral. We can see the points or the vertices A, B, C, and D lie on the circumference of the circle or on the circle. G is a point on AD. We can see point G lying on the chord AD such that BG is parallel to CD. There is BG and there is CD, and it is also indicated that the two lines are parallel. ECF is a tangent to the circle at C. There is line ECF, and then point C is the point of tangency, or it is the point of contact between the tangent and the circle. Angle GBD is equal to 30 degrees. Angle DCE is equal to 60 degrees. They are indicated in the diagram. Angle GBD is indicated in the diagram as angle B2, and angle DCE is indicated in the diagram as angle C1. Now let us move. Having the line BG parallel to line CD, we can see that angle D1 is equal to angle B2 because these angles are alternate angles, which means that the magnitude of angle BD1 is equal to 30 degrees. And then we indicate in our diagram that angle D1 is equal to 30 degrees. Right. Moving forward now, looking at triangle BCD and the tangent ECF given, we can see that when the tangent intersects the circle at point C, there is an angle that is subtended between the tangent and a chord, and that angle is angle C3, which we can say angle C3 is equal to angle D1. For the reason being is we are applying the tan chord theorem. So angle C1 is equal to angle D1, which means that the magnitude of angle C1 is 30 degrees. Right, looking at the straight line with angle C1, C2, and C3. So we apply the theorem which says that the angles on a straight line add up to 180 degrees. So meaning that the magnitude of angle C2 in this case is 90 degrees. The magnitude of angle C2 is 90 degrees. Reason, angles in a straight line, they are supplementary. Right, if now looking at BD, now you are having an arc there which subtends angle C2. Now the angle that is subtended by this particular arc is 90 degrees. It makes now this chord or an arc to be, it makes this arc to be a semicircle, and then it makes this chord be a special chord, which we may say the chord is a diameter because it subtends an angle of 90 degrees on the circle. Right, still looking at triangle BCD, you can see that you're having three angles there. You have angle D1, you have angle C2. Then now we are looking for the magnitude of angle B1. We can say angle B1 is equal to angle C1. Reason, you are applying the tan chord theorem because there is an angle subtended between the tangent and a chord. So the magnitude of angle B1 is 60 degrees. Right. Now moving forward, looking at angle A, we can say angle A plus angle C2, they add up to 180 degrees. Then therefore it means that the magnitude of angle A is 90 degrees. The reason is that the opposite angles of a cyclic quad are supplementary. Looking at the quadrilateral, ABCD. Then therefore the magnitude of angle A is 90 degrees. Alternatively, you would say that the magnitude of angle A is 90 degrees. Reason is the angle in a semicircle, because now we know that the chord BD is a special chord called the diameter. Then therefore the magnitude of angle E is 90 degrees. Either you use the theorem which says opposite angles of a cyclic quad are supplementary. Then you get angle A as 90 degrees, or now you know that angle A is subtended by the chord BD, which is a special chord called the diameter. Then therefore you can say angle A is equal to 90 degrees, which is the angle in a semicircle. Then therefore that is it. Thank you.